Swayam Prabha. Digital India. Educated India.
Hello viewers, welcome back to the course, to the lecture on the stability of slopes. We had started this particular topic on the last turn and we had discussed about the types of the slopes. Then we discussed the different considerations, what is mechanistically we mean by stability of slope. We discussed about the limit equilibrium method. Limit equilibrium method means we consider some failure plane, a potential failure plane is considered, and on that potential failure plane we find out what are the shearing stresses, what are the mobilized shearing stresses and what are the available shearing strength. The ratio of the shearing strength and the mobilized shearing resistance, that gives the factor of safety. Then we discussed about the shear strength parameters. The Mohr-Coulomb parameters C and phi in general will be used. We also discussed about the use of maximum versus ultimate strength. In case of the clays, the shearing strain has an influence on the shear strength parameters. For high strains, it has been found that the strength becomes low. So, it was suggested that especially for the over consolidated clays, not to use the maximum value of the shear strength parameters, rather to use the ultimate strength. Then we also discussed about the plane strain condition. Plane strain condition means we had considered the slope to be in 2 dimension and perpendicular to the plane of paper, unit length is taken, and it is considered that there is no deformation which is occurring in the 3rd dimension, and this particular assumption gives somewhat conservative results that we should keep in mind. Let us now discuss the next consideration, the rupture surface. As I told that in the limit equilibrium analysis, we assume a failure plane, potential failure plane, and on that failure plane, for failure all the shearing strength along the rupture surface must be overcome. So, this is the assumption that along that failure plane the shearing strength should be exceeded. If it is exceeded, then and only then the failure will be taking place. And secondly, there are infinite number of potential failure planes which are possible. So, there can be infinite number of potential failure surfaces. We have to search for all of them, and then failure occurs along the critical surface having minimum factor of safety. As per this procedure, our intention is to find out that particular surface along which minimum factor of safety is obtained, and that particular surface is considered critical. Now, let me go to different types of the safety factors. Safety factors means it gives you an idea about the margin of safety. Let us consider that there is a plane and shear strength parameters are C dash and phi dash. Then the maximum shear strength which will be available is tau f is equal to C dash plus sigma dash tan of phi dash. Please note, we are doing effective stress analysis. So, this is the maximum shear strength from the Mohr-Coulomb criterion. And let us say tau is the average value of the mobilized shearing resistance, means if you resolve the forces and find out what is the acting shear stress, that is tau. Then factor of safety is defined as factor of safety with respect to shear strength. First of all, I am taking this particular factor of safety, I am designating it as Fs. This will be equal to the ratio of maximum available shear strength. This is the shear strength, which is the maximum available value of this strength, and tau. Tau is the average value of mobilized shearing resistance, or you can say what is being acted upon there. So, this is the shear stress which is acting, this is the shear stress which is available. So, if I put these values C dash plus sigma dash tan phi upon tau, this gives me a margin of safety. This tells us, this gives the idea how safe this particular plane is. So, this is defined as the factor of safety with respect to shearing strength. As the acting shear stress is tau, it is not equal to tau f, it is less than tau f for a stable plane. Then it can be written as, from this equation, if I take tau on this side and Fs on this side, so I can rearrange this equation and the equation becomes tau equal to C dash upon Fs, Fs is the factor of safety, plus sigma dash tan of phi dash divided by Fs. This equation now I can write in little bit different manner. I now define mobilized cohesion and mobilized friction angle. I define them like this: Cm, or sometimes I can write Cm dash also. Cm is equal to C dash divided by Fs, and tan phi m I am writing tan phi dash divided by Fs. In fact, these parameters Cm and phi m, they are mobilized parameters, means when the slope is stable, the mobilized value of cohesion and mobilized value of angle of shearing resistance, or you can call it angle of internal friction, will be this much. This will be phi m and this will be Cm. So, if I define them like that, then this equation tau equal to C dash upon Fs, I replace it by Cm dash here and here sigma dash tan of phi m. So, this is the new equation I am getting in terms of mobilized shear strength parameters. Now, if the factors of safety with respect to cohesion and friction are different, then mobilized shearing resistance will be this much. See here in the previous equation, instead of Fc here it was Fs, we had taken, as per our definition, we had defined Cm is equal to C dash upon Fs and tan phi m equal to tan phi dash upon Fs. This value we had taken same, but in the field you can take them different. See what happens in the field is factor of safety is basically used to have more confidence in the work. For example, if we have calculated, we have measured C dash value, we have obtained phi dash value also. So, if our confidence in C dash is small, then we should use higher factor of safety. If our confidence is large, if I am sure that phi dash value or C dash value or this parameter whatever I am getting is likely to be the same, I am having more confidence, then I will be using lesser factor of safety. So, depending on the confidence in these parameters on C dash and phi dash, we can use different factor of safety. In fact, on phi you can use a smaller amount of factor of safety, because phi value we can obtain more confidently. So, if I use different values of the factor of safeties for cohesion and friction, then tau will be equal to C dash divided by Fc. So, this is Cm plus sigma dash tan phi dash divided by Fq. So, this will become tan of phi m. So, remember Cm will be equal to C dash upon Fc and tan phi m will be equal to tan phi dash upon Fq. where FC and FC and Fy are the factors of safety with respect to cohesion and friction respectively. So, we have defined the factor of safety with respect to strength, factor of safety with respect to cohesion, factor of safety with respect to angle of internal friction F phi. Now, there is another factor of safety which is sometimes used is factor of safety with respect to height. You can understand it this way, that there is a critical height of a slope. This is the maximum height at which it is possible to keep a slope stable. You cannot have a slope more than that height and it will remain stable. If the height becomes more than critical height, it will become unstable. So, there is always a maximum value of the height for which it will remain stable, and factor of safety with respect to height is defined as that critical height, means that maximum value of the height, that maximum value which the height can attain divided by actual height which is present there. So, if it is a stable slope, in case of stable slope, what is going to happen is critical height will be more, actual height will be less. So, FH, factor of safety with respect to height, will be more than 1. In case critical height is less and actual height is more, that means factor of safety with respect to height is less than 1 and it is going to fail, it cannot remain stable. Let me try to solve some examples to give you the idea which we have discussed about the factors of safety. This is a problem given to us. Shear strength parameters of a soil are C dash equal to 30 kPa. So, we are doing the effective stress analysis all the time. Phi dash is equal to 15 degree and it is given Cm dash is also given, the mobilized cohesion. It is 18 kPa, kPa means kilonewton per meter square, and phi m dash is also available 12. So, you can see here phi dash is 15, phi m dash is 12, C dash is 30 and Cm dash is 18. So, mobilized values of the shear strength parameters are less than their actual values. So, means the slope is stable. And it is given to us that the average value of the effective normal stress sigma dash is 100 kPa, and we are required to find out factor of safety with respect to shear strength, that is number 1, with respect to cohesion and friction, and also we have to work out the extreme values of Fc and F phi for which this particular slope will remain stable. This is the solution. Let us first calculate the average shearing strength. Shearing strength means what is maximum available shear strength, what is the maximum amount of which can be made available. So, tau f will be equal to C dash plus sigma dash tan of phi dash. C dash is 30, sigma dash is 100, phi dash is 15, and when I put these values, tau f comes out to be 56.79 kPa. So, this is the average shearing strength, maximum strength. Now, average value of mobilized shearing resistance. See what is being mobilized. Cm and phi m give us what is the shear strength that is being mobilized. So, it is being mobilized tau equal to Cm dash, same equation, instead of C dash put Cm dash, instead of phi dash here put phi m, or you can call it phi m dash also. So, Cm dash plus sigma dash tan of phi m dash, Cm dash is 18, sigma dash is 100, phi m dash is 12, and you get the mobilized shearing resistance 39.25. Now, please note this is the mobilized. Mobilized means we are applying, or the slope is being acted upon this much by this much stress, whereas available is this much. So, available strength is higher than the mobilized shearing resistance. So, that means the slope is stable. And how to calculate the factor of safeties? It is very simple. Factor of safety with respect to strength is its available strength upon mobilized strength. Mobilized will be equal to applied stress. So, 56.79 divided by 39.25 and the factor of safety is 1.45. In fact, in case of the slopes it should be around at least around 1.5. So, you can say it is just at the verge, it is just stable slope. And if you calculate the factor of safety with respect to cohesion, this is the ratio of C dash. C dash means maximum value of the cohesion that can be made available divided by the mobilized value of cohesion which we are mobilizing or which the structure is mobilizing at present, and this will be equal to 30 upon 18. It comes out to be 1.67. Same way, factor of safety against angle of internal friction, it is equal to tan phi dash. It is a measure of the maximum available frictional resistance, and tan phi m, this is the mobilized frictional resistance and their ratio. So, it is 1.26, 1.67 and 1.45. So, the slope is stable. Now, in the second part of the question, it is required that we should get the extreme values of f c and f y for which the slope is stable. In fact, you can work out large, or I should say infinite number of combinations of f c and f y for which the slope will remain stable. I again use the same equation, tau is equal to, this is C mobilized plus sigma dash tan phi mobilized. So, to get extreme value of f c, the minimum value of f c and f y, you can say, let me explain that. Minimum values of f c and f y for a stable slope should be 1. So, if it is less than 1, then we will assume that it is going to fail. If it is less than 1, then also it is going to fail in friction. So, the extreme value of, to get extreme value of f c, put f phi equal to 1. So, put f phi equal to 1. Similarly, to get maximum value of f phi, put f c equal to 1. So, here mobilized shear strength was 39.25 and C dash, I am putting f c equal to 1 and putting f phi is as unknown, and when I put these values, sigma dash is 100, I get f phi equal to 2.89. So, this is the extreme combination. This is one extreme combination. That means, f c will be equal to 1 and f phi will be equal to 2.89. The another extreme combination is obtained by putting, you can see in this equation, it is again the same equation, C dash upon f c plus sigma dash tan phi dash upon f phi equal to mobilized shearing resistance. So, 39.25 is equal to C dash upon f c. Now, I am putting f c as unknown and I am putting the lowest value of f phi. So, 1 here. So, when I put it as 1, the extreme value of f c, sorry, it should be f c here, that comes out to be 2.40. So, similarly, you can work out all the combinations, different combinations of f c and f phi can be worked out. Now, let me go to the next part of this particular chapter, the infinite slopes. And first I am taking infinite slopes in sand. Sand means it is a granular material, its cohesion is 0. So, C dash is equal to 0. It is an infinite slope. So, this is the ground surface, it is extending up to very large distance. So, for theoretical purposes we will be taking it as infinite, it is just like a hill slope. And here I have taken a plane of rupture. You can have it, in fact, in case of the hills etc., there are there is a hard stratum available at certain depth. So, we can use that stratum also. So, this is the surface at which we are considering the stability. To consider the stability, I am taking this a slide A, B, C, D. Its weight is acting in downward direction, and here at the base it is trying to slide down. So, the frictional force is acting in upward direction, and reaction, because of weight there will be reaction is acting in this direction, and normal stress will be acting in this direction. This will be acted upon forces from downstream side as well as from upstream side, this P1 and P2, these two forces, but their values will be same and their line of action will also be same. So, as far as this analysis is concerned, we are not considering them. So, let us take a point at this depth. The unit weight of this material is gamma, and the depth of this rupture surface is, let us say, Z. Then I can find out the vertical stress which is acting at the base of this slice. This will be equal to gamma into Z. Gamma is the unit weight, Z is the height. So, Z into B cos beta. B is this dimension. Please note, we have taken the dimension B as the inclined dimension. So, the thickness, the horizontal, this horizontal dimension will be equal to B into cos of beta. So, B cos of beta is this horizontal dimension, Z is vertical dimension. So, B cos beta into Z, that gives me the volume, and when I multiply it with gamma, this gives me weight. So, weight of this particular body A, B, C, D will be gamma Z B cos beta into 1. This is the area, sorry, B cos beta into Z, this gives me the area, and I am taking 1 unit perpendicular to the plane of paper. So, volume will be Z B cos beta into 1 and multiplied by unit weight, that gives you the weight. So, total weight is equal to gamma Z B cos beta into 1, and the area over which this weight is acting is B in this direction and 1 perpendicular to the direction of the perpendicular to the plane of paper. So, the vertical stress will be gamma Z B cos beta upon B. So, this B will cancel, and vertical stress at a depth Z will be equal to gamma Z cos of beta. So, this vertical stress will be acting in vertical direction. I can resolve this vertical stress in two components. One component will be normal component, which will be acting normal to the plane of the rupture, and second component will be parallel to the plane of rupture. And if you remember, when I was discussing the basic mechanism of the slope failure, this is what we did. The component of weight that is trying to create instability will be that component which is along this tangential direction, and the component of weight which is perpendicular to the plane of rupture is going to give you stabilizing force. So, here normal component will be equal to gamma Z cos beta into cos beta. You can see here this line is having this line is inclined at an inclination beta. So, thus normal to the rupture and vertical, they will be having beta angle in between them. So, the normal component will be equal to sigma dash equal to gamma Z cos square beta. This will be the normal component of the vertical stress. Whereas, the tangential component, the component that is trying to create instability, that will be along the rupture plane, and it will be equal to this value gamma z cos beta and into sine of beta, this sine of beta. So, shearing stress will be equal to gamma z cos beta sin beta. So, now we have got the shear stress on this plane, we have got the normal stress on this plane. Let us get the shear strength along this plane. As I told you, shear strength is the maximum strength which will be available. So, tau f will be equal to C dash plus sigma dash tan of phi dash, and we are taking first example as the sand. So, C dash is equal to 0 in case of the sand's cohesion is 0. So, tau f will become sigma dash into tan of phi dash, and when I put the value of sigma dash from the previous slide, you can see sigma dash was gamma z cos square beta. So, tau f will be equal to gamma z cos square beta into tan of phi dash. So, this is the shear strength, this is shear strength available, and the shear stress which is applied is this much, or you can say this is the mobilized value of the shearing resistance. So, the factor of safety with respect to shearing strength F s is defined as the ratio between the shear strength and the shear stress tau f upon tau, and when you divide this value by the tau value, this equation reduces to a very simple form, F s is equal to tan of phi dash upon tan of beta. So, it is a very simple equation which we finally obtain, and you can see if I put phi dash, if phi dash is less than beta, this F s value will be less than 1. If phi dash is more than beta, this F s will be more than 1. In other words, if the angle of shearing resistance is higher than this, it will be stable. So, for a slope to be stable, the maximum value of its inclination, the maximum value of its inclination with the horizontal may be equal to phi dash. So, this is a thumb rule which we can remember, that if it is a cohesionless soil and it's a and the ground is making beta angle, then beta should always be less than phi dash for the slope to be stable. Let me now consider the next case, which is more general. It is an infinite slope. Last time we had considered only the sandy soil, C was 0, but now it is a general case, C phi soil. And here it is again the same thing, an infinite slope which is making angle beta, and our analysis will assume, and it has been observed in the field also, that plane of rupture is generally horizontal, is generally parallel to the ground surface, or if there is a hard stratum available here, we can take that hard stratum also. At that particular stratum, we can take this plane of rupture and then do the analysis. Similar to previous case, I am taking this body, the one slice, it is having weight W, and weight W is acting over here. I can find out the vertical stress, and this vertical stress is again resolved into tangential component as well as normal component. Tangential component is going to create instability, the normal component is going to give you higher frictional resistance, and then we are going to get factor of safety. Let us say the depth of the rupture plane here is h. So, the vertical stress at that rupture plane is given as gamma into h, h is the height of this slice, and into cos of beta. So, gamma h cos beta, as in previous case, this is sigma v. and its normal component, normal means normal to the plane of rupture. So, normal component will be gamma h cos beta, means sigma v into cos beta. So, that becomes gamma h cos square beta. Its tangential component, the shearing stress which will try to create instability, tau will be equal to this value into sine of beta. So, gamma h cos beta sin beta. Similar to the previous case, to get the factor of safety, we need to know what is the maximum available shearing strength at this rupture plane. So, tau f will be equal to C dash plus sigma dash tan of phi dash. So, tau f will be C dash, sigma dash is from here gamma h cos square beta into tan of phi dash, and when I put this in this equation, factor of safety is shearing strength divided by available the mobilized shearing resistance or applied shearing stresses. So, here it will be C dash this value tau f divided by tau. So, when I put them, C dash plus gamma h cos square beta tan of phi dash upon gamma h cos beta sin beta. This is the value of the factor of safety for C phi soil. Now, this is an interesting case here. Let me plot here, this is x axis, I am plotting sigma, and y axis I am plotting the shear stress. And from origin, let us plot a line at an angle beta. Beta is the inclination of the slope. And here this is the failure envelope, which is given by Mohr-Coulomb criterion. On y axis, it is having an intercept C dash and it is having an inclination phi dash. Now, if I take one in this range, let us say I take a line AB and I represent this line AB by the vertical stress sigma V, then OA, this is the horizontal component, this is sigma V into cos of beta. OA is from this figure, it is equal to sigma V into cos of beta. And if you remember in the previous figure, sigma V into cos of beta was nothing but sigma dash normal stress. So, here OA is equal to sigma V cos of beta. So, this intercept represents sigma dash, the normal stress which is acting over the rupture plane. Similarly, I can show that AB will be equal to sigma V into sine of beta, and from previous figure again this should represent the shearing stress. So, AB represents AB, capital A, capital B, this represents the shearing stresses. So, here in this diagram, if this is vertical stress, then OA is going to give you the normal stress and AB is going to give you the shearing stress. And also, what does AC give? AC is nothing but it is tau f, it is equal to C dash plus sigma dash, this is sigma dash into tan of phi. So, in fact, this line, any point on this line gives you tau f. So, AC represents the tau f. Now, the factor of safety, as I told you, was tau f upon tau. So, in this diagram, I can write the factor of safety will be equal to AC upon AB. This is an interesting case and it will give us very important conclusions. Let me take different cases. The first case I am taking when this beta is more than phi dash. This is the general case in fact with which I started. So, as I told you in the previous slide that F s is equal to A c upon A b. So, this ratio A c upon A b, this ratio gives you the factor of safety. Now, if O A is within this range between O and F, if O A is less than O F, in that case A c will be more than A b. So, for up to this point E, this A c is more than A b. That means, the shear strength available is more than shear stress being applied. In other words, F s is the ratio of these two straight lines, these two values A c and A b. F s will be equal to F s will be more than 1. That means, it is a stable slope. So, if sigma dash represents the normal stress, it is within this range O to F, then F s will be equal to, it will be less than 1. It will be more than 1 and the slope will be stable. When A point reaches at F, so here A c and A b both will be equal and it will be a limiting case. So, factor of safety is exactly equal to 1, it is just at the verge of failure. And if sigma dash, if this point O A comes somewhere here, in other words, if sigma dash is this much, sigma dash is higher, then the factor of safety will be less than 1, because now you will be taking ratio of this and this. So, it will be unstable because factor of safety will be less than 1. So, this is an interesting case here for certain region in this region when the normal stress is up to this value, the shear strength is more, whereas in this region beyond E, shear stress is more. So, it will be unstable. So, what we infer from this, what are the conclusions? Conclusion is that if H is less than certain critical depth, let me go back here. Here the normal stress, as you go on increasing the normal stress, what does it represent? It represents that the weight is increasing, or in other words Z is increasing, the depth is increasing. So, at higher depth, if the value of depth is large, then factor of safety is less than 1. So, if this depth of the slope, this h value is less than certain critical value, it is going to remain stable, because sigma dash will be less than that particular critical value. If h is more than particular depth of particular value of the depth that we are calling here as critical depth, then this will represent an unstable slope, where h is the depth of the hard stratum. So, the conclusion is, if the depth of the soil layer is more than critical depth, it will be unstable. So, what it gives us is that, suppose there is a hard stratum here, and if the stratum is at a relatively shallow depth, this h will be small. If h is small, sigma dash will be small, that means there are chances that the slope will be stable. But if the hard stratum is available at a large depth, then it may become unstable. So, finally, it is concluded, if the slope is steeper than angle phi dash, remember we had taken a case where the slope was steeper than phi dash, then it will be stable only up to certain critical depth. Beyond that, it will not be stable. Let me now go to the case number 2. The relationship between beta angle and phi angle, and here again this beta angle shows the inclination of the slope angle, and this is the phi dash. We can again get this expression that factor of safety is equal to AC. This point is A, this point is C, and upon AB. The factor of safety with respect to shear strength will be equal to this much ratio. Now, let us see what happens if I go on increasing, if I keep on changing point A from 0 and let us say up to theoretically let us say up to infinity. So, for each OA, now you can see AC upon AB, I am trying to find out for different values of sigma dash, and here these two lines are parallel to each other because we have taken beta equal to phi dash. So, it is a slope, we are analyzing a slope which is having slope angle exactly equal to phi dash. So, what is going to happen? At each value of OA, means at each value of sigma dash, Fs will always be more than 1. See, whether you take the point here, whether you take the point here or you take the point here, this ratio is always more than 1. And when this value becomes, when sigma dash becomes smaller and smaller, if you take a point somewhere here, if you take a point somewhere here, then this ratio is very large, and theoretically if I take sigma dash is equal to 0, then this factor of safety in fact becomes infinity. But as you go on this side, as you go on increasing sigma dash, this Fs value will go on reducing from infinity to some definite values, and finally at a very large value of sigma dash, this Fs will approach towards unity. So, for very high depth, very deeper slopes, Fs will be approaching towards unity, and for shallow depth it will be very high factor of safety. Let me go to now case number 3rd. First we had considered when the slope was steeper than phi dash. Second case we had considered when slope is exactly equal to phi dash, and in first case when the slope beta was steeper than phi dash, we had concluded that only up to certain depth the slope is going to remain stable. Means if the hard stratum is available at a shallow depth only, slope will remain stable. Whereas, in the second case when beta was equal to phi dash, at all depths it was stable. And now, let us see what happens in third case. Now, the slope is very flat, beta angle is very small, this is phi dash is larger, and now you can check it again. Fs will be equal to AC upon AB. Again, this is the shear strength, A to C, and A to B, this is the shear stress. Their ratio represents the factor of safety, and again the same thing happens when sigma dash is very small, this value tends towards infinity. Factor of safety, if I take theoretically at point O where sigma dash is 0, you have AC equal to C dash and AB equal to 0. So, factor of safety at this point will be almost infinity, but as you go on increasing it goes on reducing, but because the ratio they are not parallel to each other. So, we cannot say what happens at very large value, but one thing is sure that whatever value you may take for sigma dash, it may be a very large value, but this factor of safety is always going to remain more than 1. So, the conclusion is if the gradient of the slope is less than phi dash, then slope is stable for all depths. So, for all depths it will remain stable. Now, we can calculate some important parameters. For example, critical depth. Critical depth is that depth for which the slope will remain stable. So, considering the first case which I took when the slope was steeper, beta was more than phi dash, and considering the limiting case, when I say critical depth means the maximum depth for which the slope will remain stable, or if it is the depth at which the hard stratum should be available, otherwise the slope will not remain stable. So, considering the limiting case, at limiting case means when tau f is equal to tau. What we mean by this? The entire shearing strength which is available, it is being mobilized. So, you will be getting the maximum depth. So, this is the critical depth h c. So, we can now use these values we have already derived. Tau will be equal to gamma into h cos beta sin beta. In place of h, I am putting now h c, and for the strength, shearing strength, it will be c dash plus gamma h c cos square beta tan phi dash. This is the same equation which we used in the case number 1. So, from here c dash will be equal to gamma h c cos beta is taken common, and inside bracket you will be getting sin beta minus cos beta into tan of phi dash, and finally you will be getting this expression h c is equal to c dash divided by gamma, take cos beta common. So, gamma cos square beta tan beta minus tan of phi dash. So, using this expression you can find out the critical depth, the depth which gives you maximum value of the depth for which the slope will remain stable. There is another important quantity which we call as stability number. Again, if I consider the same case when beta is more than phi dash and slope is stable, then the mobilized shearing resistance tau, the mobilized shearing resistance is equal to tau f. So, here gamma h cos beta sin beta, this is equal to mobilized shearing resistance. So, now we are talking in terms of the mobilized shearing resistance. This is the applied shear stress and this is the mobilized shearing resistance, and from here you will be getting Cm is equal to gamma h cos of beta and sin beta minus cos beta tan of phi m, and finally you will be getting this expression Cm upon gamma h is equal to cos square beta tan beta minus tan of phi m. This particular quantity cos square beta tan beta minus tan phi m, or on left hand side it is Cm upon gamma into h. This is a non-dimensional quantity, non-dimensional number. You can see C, units of C will be the units of pressure, and gamma is let us say kilonewton per meter cube into h. So, it also becomes kilonewton per meter square. Cm is also kilonewton per meter square. So, this is a dimensionless quantity, and this quantity is known as stability number. This number is very important in analysis. During old days when the computers were not available, the computations were tedious, and this stability number was very helpful in doing the complicated computations. This stability number, as you can see, is directly proportional to required cohesion and inversely proportional to allowable height. And in this equation, Ns is equal to Cm upon gamma h cos square beta tan beta minus tan phi m. Now, if I replace Cm and phi m, Cm is the mobilized cohesion is equal to C dash upon F c. This is the definition of the factor of safety with respect to cohesion we had given. F c was equal to C dash upon C m. Same way F phi was equal to tan phi dash upon tan phi m. So, now in this equation I am replacing C m and tan phi m, and in general what we do is to define this stability number, normally we take F phi equal to 1. So, the stability number will be equal to C dash upon F c into gamma h. So, here it was Cm upon gamma h. So, put the value of Cm, this becomes C dash upon F c into gamma h is equal to cos square beta tan beta minus tan phi dash. Remember, in this equation, whenever you use this equation for some stability analysis, it is inherent, it is already assumed that f phi is equal to 1. So, this is the stability number, this is the definition of this stability number, which is very useful in the analysis of slopes. Now, let me take the another case of infinite slope with seepage. Here I will be considering several sub cases, and first case I am taking seepage through entire mass. Again, this is an infinite slope, inclination is beta, depth is h, and here is the plane of rupture on which we are considering the equilibrium, and the seepage is taking place in this direction. We are considering this slice, again its weight will be acting in downward direction. We can find out the stress acting on this plane, and then we can resolve that stress into normal component as well as the shearing component as usual, and then we will find out the factor of safety. So, the normal stress at the shearing plane will be equal to sigma v into cos of beta, and finally, this is the expression which we have been getting. The difference here is that instead of gamma, now you will be using gamma saturated minus gamma w, that means submerged unit weight, because this will be the stress which will really give the strength. So, the normal component will be equal to gamma submerged into h into cos square beta, and the shear stress, please note down here, to compute the shear stress you should not use gamma submerged, but here you have to use gamma saturated. The weight, total weight will be acting, and total saturated weight will be creating the instability. So, shearing stress will be equal to gamma saturated into h cos beta into sin of beta. Now, we are considering the slope to be stable, and let us talk in terms of the mobilized shear strength parameters. So, mobilized shearing resistance will be equal to C m dash plus sigma dash tan of phi m dash. Put the value of sigma dash here. So, it becomes sigma m dash plus gamma submerged h cos square beta, which we have taken from previous slide. So, sigma dash is equal to gamma submerged h cos square beta, and by putting this value we get tau f is equal to this much. Now, equate tau and tau f, the shearing stress which is acting and the shearing strength, then we will be getting this expression C m dash plus gamma submerged into h cos square beta tan of phi dash will be equal to gamma saturated into h into cos beta sin beta. This is the acting shearing stress. So, finally, I take the term C m on the left hand side and gamma saturated into h on the left hand side, and we convert this equation into the form of the stability number C upon gamma into h, and this is the equation you are going to get C m dash upon gamma saturated into h equal to cos beta sin beta minus gamma submerged upon gamma saturated cos square beta tan of phi m dash, and finally, you take cos square beta common. So, C m dash upon gamma saturated into h will be equal to cos square beta tan of beta minus gamma submerged upon gamma saturated into tan of phi m dash. Now, if we use same factor of safety for cohesion, for angle of internal friction, for shearing strength, then the equation, in the equation we will be replacing the parameters by this C m will be C dash upon f s and tan phi m dash will be tan phi dash upon f s, and you will be getting this equation. C dash upon F with respect to shearing strength, gamma of saturated into H will be equal to cos square beta tan beta minus gamma submerged upon gamma saturated tan of phi dash. Or if you use the values for F c and F phi which are not equal, then this equation can be written as C dash upon F c gamma saturated H cos square beta tan beta minus gamma submerged upon gamma saturated, and here you will be having tan phi dash upon F phi. In the stability number, normally we take the value of F phi as 1. So, if the factor of safety with respect to friction is 1, the stability number with respect to cohesion is given as Ns is equal to C dash upon F c gamma saturated H equal to cos square beta tan beta minus gamma submerged upon gamma saturated into tan of phi dash. So, this is the stability number we get for this particular case. So, in today's lecture class we have discussed, we started with the different types of the factor of safeties, then we started discussing the infinite slopes. We have also given some idea about the stability number, and we have given the how to analyze, how to get the factor of safety, or how to get the expressions which correlate factor of safety and other parameters in through the stability number for infinite slopes. So, in the next class we shall continue with more cases on the infinite slopes.